It's a rod diameter. Okay. Now let us say this rod diameter D is present over here. Okay. This one is your rod diameter. Okay. We represent it by small d. Now we focus on small d. After that, this one is D2. Okay. So in order to remember the notation, first of all, you must understand this diagram very well and visualize it while solving the problem. Okay. Now this one is your D. This one is your D2 over here. And where is your D1? In the top view of this diagram, this one is your D1. Okay. So in front view, where we represent D1, this is D, this one is D1, then this one is D2, then this one is D3, and this one is D4. Okay. So it's in a sequence. Okay. If you understand the diagram, then D1, D2, D3, D4, it's in a sequence. Okay. Likewise, horizontal dimensions. This one is A. Okay. After that, the Cotter with B and the value of C. Okay. So horizontal are also in a sequence A, B, C. Then this one is D. This one is D1, then D2, then D3, the spigot collar diameter, and D4 socket collar diameter. Understand? Then all of you are aware about this, so I don't repeat it again. Then the first point, tensile failure of rod. Okay, that we discussed earlier, but once again we start with the first point, tensile failure of rod. Each of rod diameter D subjected to tensile force. Now, from where we get that sigma T in an actual problem, the value ultimate tensile stress of the material used for the rod is given. Okay, from that you divide it by means of factor of safety and you get sigma T. Sigma T is permissible tensile stress for the rod. Now rod is having cross section area, circular type of cross section area. Okay, so generally P that force applied, tensile force divided by cross section area. Okay, from that which value that we require to find out, value of D. Okay, this is very simple thing. Now once you get value of D, you move to the next step, tensile failure of spigot. Okay, now into that, the spigot over here represent, let's see this one. If we take a XX plane, we take a section over here, then this much of the area, the shaded area, okay, over there, total tension get occur. So in last lecture, we also discussed why we not take up exact circular cross section area, because if there is change, if there is reduction in area, then the stress get more. So where there is a change in cross section area, that particular cross section area we take into consideration for the calculation. Okay, so let us consider this much of the area. How we calculate this? Pi by 4 into d2 square. Okay, let's focus over here. It's the actual cross section area. Pi by 4 into d2 square, total circle, minus the rectangular area d2 multiplied by t. Okay, so the area represent pi by 4 into d2 square minus d2t subjected to tensile force P. So that value over here is what? This value, this equation. Now into that value of T is unknown. Now for that value of T, you must consider in every type of problem, you consider T is equal to 0.31 into D. Okay. Understand this thing? Am I audible to all?
Yes, sir.
Okay. Now let's move to next slide. Tensile failure of socket. Socket is also subjected to tension, but this area of the socket, because socket is having some hollow circular cylindrical part. Okay. So let's say the figure shows the weakest section at YY. Now where is that YY? This one. We take a cross section, or we take a section over here. Okay. Then the socket end, which is subjected to tensile stress, and the corresponding area regarding that, this much of the area that we represent over here. Okay. Outside diameter D1, then the inside diameter over here is D2, and T is the thickness of your quarter. Okay. So pi by 4 into D1 square, pi by 4 into D1 square. This whole circular cross section area minus pi by 4 into D2 square. So we get one ring over here, and out of that we neglect or we minus this much of the area. This much of the area we require to minus. So that area is what? D1 minus D2, means the whole, the length multiplied by the thickness of the quarter. Okay. So this is the circular area, and from that equation, which value that you require to find out? Value of D1. Okay. Now let's move to the next slide. Find the value of B. B, it's a width of your quarter. Okay. And it is subjected to double shear. Okay. Double shear, the figure represent over here. So this much of the part is present inside the spigot, and this much of the part is inside the socket. Okay. So spigot stretch the quarter towards right, and the socket stretch the quarter towards left. So because of that, the shear get take place at the upper part of the quarter as well as the lower part of the quarter. In order to understand this very well, let us consider the quarter is made up of a very low strength material, and spigot and the socket is made up of very high strength material. Okay. So if the actual load P is get applied, then this much of the part, okay, is come up with the spigot. Okay. And these two parts, okay, goes with the socket, and actual shear is take place along that area. Okay. So from that double shear take place, the shear area, if we see it in a top view, then B multiplied by T, along that area shear take place. It's a direct shear stress. Okay. Two areas are there, that's why we multiplied by 2. Okay. Why 2 is there? Because shear take place on two areas having same cross section, B multiplied by T. So tau is equal to P divided by 2 multiplied by B. Now what is permissible shear stress for the quarter? Now whatever the material given for the quarter, okay, divide by the factor of safety, you get tau permissible, okay, from the problem. Now B required to find out by two equation. First is this direct shear stress, and second is bending stress of the quarter that we discuss later. Okay. So first of all, required to remember, we find the value of B twice, and out of that the bigger value of B is considered twice, from one of this direct shear stress, and another one is bending failure of Cotter that we discuss later. Understand? Now let's move to the next slide. Do all of you understand this thing? Is there any problem? No? Give me in a chat. Am I audible? Yes? Hello? Any reply? Yes? Okay. Okay. Now I require to understand if you are audible or not. Okay. Then let's move to the next slide. It's a shear failure of spigot end. Okay. So shear failure, it's a direct shear again. Okay. Spigot. Now let us see over here into this region. Cotter is present. Okay. Along this region, what? Cotter is present over here. Okay. Now let us consider over here the cotter is now made up of very strong material and the spigot is made up of very weak material. Okay, then what happen? Cotter get shear out the spigot. Okay, along the two region. Okay, let us say this region and the back side of this exactly. Okay, so shear in a spigot take place in two areas having same cross section area. Okay, so A multiplied by D2, this much of the A, where we represent this A in main diagram. See over here. Okay, this one is your A, value of A. Okay, this value of A is required to determine in an equation of direct shear failure of spigot. Okay, so let's see over here. Tau is equal to A divided by 2 multiplied by A into D2. Why 2? Because two areas are there. Understand? Now, and over here, find a value of A from this equation. Now, let's move to the next. The shear by means of Cotter may be possible in a socket. Okay, so in order to find out value of C, okay, socket, let us say over here, the particular section area of the socket. So that area represent shear failure. Again, two areas over there on both the side. That's why in equation we multiplied by 2. Understand? And the particular area d4 minus d2, straight line d4 minus d2 multiplied by value of C. Okay, this is the area under shear. Now from that equation we require to find out value of C. Okay, we require to find out the value of C. Understand this thing? Now let's move to next slide. Crushing failure of spigot. Till we up till now we found all the values related to the spigot and socket as well as the cotter. Okay. Now we have to cross check whether whatever the dimensions that we determine in previous formula that are safe for the crushing stress or not. Okay, so that's why in this point we check sigma C. Okay, sigma C is nothing but you can say compressive strength or you may say crushing strength. Okay, so the force P causes compressive stress on narrow rectangular area. Now where that rectangular area is present? This one. Okay, on narrow rectangular area of thickness T and width D2 perpendicular to the plane of paper. Okay. The compressive stress is P divided by D2 multiplied by T. Okay. It's very simple to determine the cross section area on which the compressive stress, because P is acted over here, it get compressed this area. That's why we are taking sigma C into consideration. So this much of the value or this much of the length is, let us say, T, and this much perpendicular to that diagram. So I am representing it by means of only a point. So this total value is what? D2. Okay. Spigot diameter. Okay. So D2 multiplied by T along that area, the compressive stress, and we have to find out sigma C. Now check means what? For the spigot, a relative ultimate tensile strength is given. Okay. So divided by factor of safety, we get what? Permissible sigma. Okay. Now from this equation in a point number 7, you find out value of sigma C and check whether that sigma C is greater or less than the permissible stress given for the spigot material. If it is less, then your dimension determined earlier, okay, that are okay, that are very safe for the quarter. Okay, that's why check for sigma C. Understand this? Getting? Okay. Now let's move to next point. Crushing failure of socket. Again over here, you require to find out sigma C. Socket end, the top part, we have to determine value of D4. At that point, we require to find out value of sigma C, whether that part is safe against compressive force or not. Okay. So in actual diagram, this represent what? This represent actual top view of your socket end. Okay. This one is your socket collar. Okay. So D4 minus D2, that is D4 minus D2 multiplied by T. Along that region, the compressive forces get active. Okay. So sigma C is equal to P divided by this value. Now, this is one the standard thing that we consider, because D4 is equal to 2.4 into D. Okay. Remember, this is very important thing. In some books, D4 is determined by this formula, sigma C as ultimate tensile stress divided by factor of safety, or in some book, D4 is considered as 2.4 into D divided by sigma C, and check whether that sigma C is less or greater than the permissible stress. Okay. So it may vary depending upon problem. So all of you must remember this point. Okay. Why we take 2.4 into D over here? It's one of the standard, okay, which is stated earlier while designing the Cotter joint. Okay. D4 is equal to 2.4 into D. Now the dimension that we represent in terms of any one particular dimension of the element. Let us say D be the one dimension, and we represent D4 in terms of D. Now such a representation of the dimension is called as empirical relation in a design. Understand? Empirical relation in a design is the one of the standard. Okay, 2.4 into D. And from where we get, after lot of designing of Cotter joint, the designer come on a conclusion that after taking D4 is equal to 2.4 into D, the Cotter will not get fail. So that's why we consider that standard. Okay, depending upon the earlier design stated by the designer. Okay, now sigma C, permissible compressive stress for the socket. Okay, so understand this is very important point. Crushing failure of socket. In some problem, you may require to determine D4. Okay, at that time, one can say I am directly taking D4 is equal to 2.4 into D, but it's not like this. Okay. In a problem where it's a clear stated that you require to find out value of D4, you use this formula. Okay. And take sigma C is equal to ultimate tensile stress divided by factor of safety and find out D4 from this. Okay. But in a general design procedure, in a problem where you require to find all the dimensions of Cotter joint, you take D4 is equal to 2.4 into D and cross check it against sigma C. So this is important point to understand. Okay. Is there any problem over here? Yes, Mayur. Okay.
No, sir.
So let's move to next. Now this is the last point of design of Cotter joint, bending failure of Cotter joint. Now I earlier said that the Cotter is subjected to two stresses. One is direct shear stress that we discussed earlier. Over there we found value of B earlier. Okay. Now the second point, the Cotter is also subjected to bending. Okay. Now when the Cotter is tight in socket and spigot, it is subjected to direct shear stress. When it become loose, then bending get occur. Loose means we if we provide a clearance over there. Now where that clearance is present, let's see over here in our actual diagram. Okay, focus. This one of the clearance that we provided. Okay, this much of the clearance we provided. If we provide such a type of clearance, then this Cotter is subjected to bending also. Understand? If it is that clearance is not provided, then the Cotter is subjected to direct shear. So in order to overcome such a situation, we focus on both the type of stresses occur inside the Cotter. So which are that both cases, both the stresses? One is direct shear stress that we discussed earlier, and second one is bending. Now the force P, this is very important again. The force P between Cotter and spigot end is assumed as uniformly distributed over the length D2. Now let's we understand the diagram first. Now this one is our Cotter. Now this much of the part, okay, of the Cotter, this much of the part of the Cotter is present inside the spigot. Okay, and this much of the length is what? D2. It is represented over here. This much of the length is what? D2. Understand? Now, this much of the part of the Cotter is present inside the socket. Okay. On another end also, this much of the part is present. Okay. The force between the socket end and the Cotter is assumed to be varying linearly from 0 to maximum with triangular distribution. Okay. So let us say that represent over here. So two things inside the spigot, value of P is uniformly distributed over here, and value of P is having a triangular uh, application in a socket. Okay. Now let's move to the next slide. Generally, you know how we find out sigma B bending stress in SOM. Can anyone say sigma B is equal to what? Yes. bending stress sigma b is equal to what? Sigma b by what? Focus this one. Sigma b is equal to mb, that means bending moment multiplied by y divided by I. So in order to find out sigma b or form the equation of sigma b, we must know the value of mb, y and I. Okay. So here the quarter is treated as a beam as shown. Okay. Now x is equal to 1/3 of y. Now where that x? This one. This one is your x. Okay. X is equal to 1/3 of the value of y. Y means this total length. Okay. Now this total length is what? D4 minus this one. D4 minus D2. Okay. D4 minus D2, that means this much of the length as well as this much of the length. So in order to find out y, d4 minus d2 divided by 2. Okay, so that is the value of y, d4 minus d2 multiplied by divided by 2. So this equation represent value of y. Understand this thing? Yes or no? Give in a chat. Otherwise, I repeat.
Yes, sir.
Okay. Now we know the value of y. Now you know, in order to take the point load in uniformly varying distribution, okay, which is 1/3 from this end, okay, 1/3 from this end. So that's why we consider 1/3 of y. So p by 2 amount is acting at a distance 1/3 of y, which is given by x. Okay, so x is equal to 1/3 of y. So that's why total value of x is d4 minus d2 by 6. Okay, now in order to consideration of p over here, okay, let us say this p is acting p by 2 over here. Take 2 part from this one. Okay, p by 2 is acting over here and p by 2 is acting over here. And value of z. So what is the value of z? Can anyone tell me? What is the value of z?
D2 by 4.
Correct, d2 by 4. Value of z is what? d2 by 4. And from that, we are able to find out bending moment. Okay, see, mb is equal to p by 2